Ladies and gentlemen, welcome to SQL Server Performance Monitoring and Tuning video brought to you by SQLworkshops.com. In this video, we will talk about data compression. SQL Server supports row and page compression. This will be very beneficial if you have I/O bottleneck. For example, if you compress an index or a table or a partition, this could lead to less disk space usage, and when you access these objects, this can reduce the amount of I/Os and lead to better performance. One thing often overlooked when it comes to data compression is the CPU overhead. Let's look at an example. To practice this example along with me, you need the SQL test tool. To install SQL test tool, you can go to sqltest.org. There you can click on download link. There you can click on install SQL test, and this will install the SQL test tool in your computer. Once you have the SQL test tool installed, you can click on file, open online examples. There you will find SQL test _ data compression. This is the example we will use during this hands-on session. Here we will create a database called SQL Workshops, and we will create table 72 until table 79 to practice various scenarios related to data compression. So to create these tables, you can click on workload 4 tab, and then you can click on start current. I already created it, and then it took around 151 seconds in my computer. I did not use SSD for this example. I used RAID based disk to show you the benefit of compression by reducing the amount of I/Os. So once you created these tables, you can execute the first set of queries. Here we are going to select max value from tab 72, 73, and 74. Let me show you what are in these tables. Let's go to settings, comments, and let's copy and paste this into one of our management studio, and then we will copy one more set of queries to management studio. Here I will show you the size of this table 72, 73, and 74. The size of table 72 is 168 megabyte. This is a table that is not compressed, that's table 72. 73 is row compressed, and the average row size is 9.3 bytes, and this is 111 megabyte, and the last table 74 is page compressed. So this is using only 108 megabyte, and the average record size is 9 bytes. Let's look at how these tables were created. So here you see I'm creating tab 72, 73, and 74. All these three tables have two columns. Column 1 primary key integer, column 2 integer. So only two columns on these tables. And I'm inserting 10 million rows into this table, and the first table is not compressed. The 73 is row compressed, and 74 is page compressed. Let's look at the way the data is. So when I execute select from these tables, let's execute from the SQL Workshops database. There you see the column C1 and C2 are the same, but C1 as primary key, C2 as no index, and all tables, all the three tables have the same data, same amount of rows. So here each table has 10 million rows. Now I will execute a query to see which table, which query is faster. The first query is we are first doing a DBCC drop clean buffers, which means we clear the SQL Server data cache, and when you execute the query, it will read the data from the disk. So here we are saying select max C2 from tab 72. So select from the table which is not compressed, and select from a table which is row compressed and page compressed. To look at the performance statistics, we will start profiler, connect, and we will take the default template, and now we will start the query. So you click on workload 1 and you click on start current. This will start this workload, which has 3 queries. First it will do a DBCC drop clean buffers, and it took 6.7 seconds to complete. If you go here, 6.7 seconds, and if you look here, the first query that is not compressed took 1.8 seconds. We are doing max C2. The second query, which is row compressed, took 2.3 seconds, and the page compressed took 2.4 seconds. Relatively same amount of CPU time. Let's execute the query again. In performance tuning, it's better to have predictable performance. So we will execute again to see it is not a one-time statistics. Let's execute. It probably take the same 6 seconds, 6.7 seconds. And when we go here, you see again the table that is not compressed is faster. And as you compress by row and page, it gets slower and slower, because in this case, SQL Server has to use CPU to uncompress the data before it looks for the max value. And this leads to more CPU usage and slower performance. So it's important to consider which table to compress and which index to compress and which shouldn't be compressed. That's why Microsoft also doesn't provide a button at the database level saying compress everything, because this could lead to bad performance in some cases. Now let's look at the same example, but without the drop clean buffer. So we are going to execute the query while the data is in the cache. Let's execute the query. Let's see how long it takes. Probably not 6.7 seconds. It's 6.4. Let's execute again. And we will look at the profiler to see which query is faster. So 6.4 again. So when you look here, you see 1.7 second uncompressed table, 2.2 and 2.4, the similar amount of time spent in CPU. So 1.7 seconds and 2.4 seconds with a page compressed table. Now let's look at an example where compression brings us performance benefit. We are going to use these 3 tables, table 75, 76, and 77. Let me show you how these 3 tables were created. Let's go to our workload 4 and let's look at these 3 tables. Tab 75, 76, and 77. The first table is not compressed, the second one is row compressed, the third one is page compressed. All tables have same schema, like you see. C1 is primary key integer, C2 is integer, the C3 is character 100, so it can take up to 100 bytes. So we have the same schema for 3, and we are inserting the same data on all the 3 tables. Let me show you how the size of the table looks like when I execute this query. Here, there you see the size of the table 75, 76, and 77 is 115 megabyte. The average row size is 115, that's 100 byte character plus 2 integer plus the row overhead. And you see with the row compressed table, it is 90 megabyte and the record size is 89.9, and with the page compressed table is 65 megabyte and the average row size is 63 bytes. And let's see how is the column C3 filled in. So when I execute this query, this is how I filled in column C3 with this replicate. So when you look here, this column was defined with character 100, but it contains only 75 bytes, 75 characters. So when the table is not compressed, it will use 100 bytes. When the table is row compressed, it will use only 75 bytes. In SQL Server, when a table is row compressed, it will store all the fixed length data into variable length under the storage. This is transparent. It is done under the storage, but your schema doesn't change. It stays the same. It says character 100, but underneath it will store it as variable length column. For example, if you have an integer which takes 4 bytes, but if you store only 1, it doesn't need 4 bytes. So it will use 1 byte to store that integer in the disk. So same way, it uses only 75 bytes to store this character 100 column. That's why you see here 89. So 75 plus 2 integer column and the row overhead. And if you look here, the first 25 characters are the same for all columns of C3. So what this leads to is prefix compression. In SQL Server, when you do a row compression, it will store all the fixed length columns into variable length column in the storage. And if you have a page compression, in addition to row compression, it will do prefix and dictionary compression. Dictionary compression means if there are the same value on the page in many places, it will store that value once in the header, and it will have a pointer pointing to that header for all columns. And if you have a prefix compression, for example, in this case, 25 characters are the same, it will save the 25 characters one time in the header of the page, and every row will point there, saving a disk space. So this is why a page compressed table is using about 50 bytes to store this character 3 column, because this 25 characters is the same for all the rows. So that's why you see average record size is around 50 bytes for this character column, plus you have this 2 integer and the row overhead. So let's execute the select statement to show you what data is here. All 3 tables should have similar data. We use the same insert statement. Now we will execute the select statement in workload 2. So workload 2 does a drop clean buffer, and it selects from tab 75, 76 and 77. So this is the uncompressed table, row compressed and page compressed. It is looking for C2 equal to 10. We don't have an index yet on column C2. We will create it later. Right now we don't have a index on C2, so it will lead to a table scan, and we will look at which query is faster. So click on workload 2 and click on start current. Start current means you are starting the current workload. So it took around 798 milliseconds. Let's execute it again. Start current, 696 milliseconds. Let's do start current. Maybe first time SQL had to prepare a plan. Now we have predictable performance. 680, 690, 642, 634. Let's look at the performance. There you see, this is the table that is not compressed. SQL uses 231 milliseconds to execute this query. And when the table is row compressed, that is tab 76, it uses 179. And when the table is page compressed, that is tab 77, it uses 180 milliseconds. As you see here, the number of reads decreases as the table is row and page compressed, leading to better performance. You see, but the CPU usage also gets higher as the table is page compressed and row compressed compared to uncompressed table. So here is a benefit where you compress the table, it uses less storage space, and when you access the table, the query is faster because of reduced IOs. What happens when you remove this drop clean buffers? Now the data is going to be in the cache, and we will execute the query to see which query is executing faster. So the query executes around 300 milliseconds, around 300 milliseconds. Now we look in the profiler. There you see the first query completed in 67 milliseconds. That is tab 75. That is the uncompressed table. And then with the row compressed table 76, it is 89, and then 130. That's the page compressed table. So when the data is in the cache, SQL has to expand the data every time before it accesses the data, and this leads to CPU overhead and hence the slower performance. Let's look at one more example here. I create 2 more tables. One is tab 78, the other one is tab 79. Both tables are not compressed. You know, the data compression is none. Both tables are not compressed. The schema is the same as tab 75, 76, 77, except the size of the character column. So we have C1 integer, C2 integer. I have character 75 if you remember, the character column, it used 75 bytes because 25 bytes we didn't fill in. And if you take the page compressed table, there was 25 characters with same prefix, so it probably used around 50 bytes to store this character column in the disk. So I manually create two tables with the same amount of rows. So we will end up with tab 78 taking similar disk space as tab 76. This is a row compressed table, uses 75 bytes. I create an uncompressed table using 75 bytes, so they will have nearly the same space. And we have tab 79 uses character 50, and here it's a page compressed table, will also use around 50 characters to store because of the 25 free space that we don't store data, and the 25 characters with the same prefix stored once in the header page. So we will have table 77 and 78 end up using similar space, except these two tables are not compressed. Now we will compare the performance. Now we will go to workload 3, and this is tab 76, the row compressed table. We will execute this query 10 times with max C2. Start current. We will look at it. The performance of this query is around 242 milliseconds. I use milliseconds here. If you want to choose milliseconds, you go to tools and click average DB time in milliseconds. Then you will have the output in milliseconds. So we will do a start current again. There you see the average time is around 236. The average time is around 242 milliseconds. Now we will use a table that is similar in size. I will show you this table here. So we'll execute this query, which shows us the size of tables. So here you see tab 76 is using 90 megabyte. Tab 78 is also using 90 megabyte. The row size is very similar. The row size is very similar. This table is row compressed. This table is not compressed, but they end up with a similar disk space usage. Now we will execute this table 78. We will do the same query. The only difference is the table size is the same, the number of rows are the same, except here the table is not compressed, so there is no CPU overhead. So when you execute this query, there you see it's not 240, it's 184. Let's execute again. It's 190 or 188. So now we will execute the other query, that is tab 77, that is page compressed, and we will compare it with an uncompressed table with a similar size. I will show you why we are doing this, because Optimizer does not cost the overhead of CPU related to expanding this data. So when you execute this query, you look here, 285 milliseconds, 83 milliseconds. Now we will use the table that is not compressed with similar size. So when I execute, it goes back to 183, the one we saw before, 183. So the interesting thing is, if you go to the script that you copied from comments, right? It's the script that we copied from comments. So if you go here, I am selecting from tab 76 and tab 78, similar to what we did in this workload 3. So what I am going to do is show you the estimated execution plan. So we will click on the estimated execution plan. There you can see the first query, which is selecting from tab 76. SQL Server thinks it costs around 10.1. And if you go to the next query, here tab 78, SQL thinks the cost is again 10.1. The table size is the same, the number of rows is the same, except the second table is not compressed. So if you look at the CPU cost, you look here, the CPU cost is 1.10016. And if you go to this table, which is not compressed, and you look here, CPU cost is 1.10016. So SQL Server thinks the CPU cost is the same for both tables because they have same amount of pages. So it looks, oh, I look into these tables, they have same amount of pages, it's going to cost the same. It does not include the cost related to expanding the data. Let's look at these two queries. Let's look at 77 and 79, page compressed and uncompressed, but same size. Let's look at the execution plan. There you see the cost is 7.7 and the CPU cost is 1.10016. And if you look here, again the cost is 1.10016. So if you execute both of these queries, of course in the profiler you can see the execution time 0.23, that is the compressed page compress, and this is uncompressed, quite different. But SQL thinks they will cost the same because it does not include the cost related to expanding the data. And we will execute these two queries, 77 and 79, 77 and 79, that is the page compressed and uncompressed. Again you see 286, 183, 286, 184, quite significant, but SQL thinks these two queries will cost nearly the same. Now let's look at an example where we create an index. So we create the index on column C2 and we are going to execute a query that will use this index. That's a possibility to use this index. So we'll create this index. And here I am selecting from this table 75, that's the uncompressed table, where C2 is less than 375. I'm going to do this on table 75, 76 and 77, that is uncompressed table, row compressed table and page compressed table. Let's look at the execution plan. In the first case, SQL Server thinks, well, it is better to use the index. The table is very big, scanning is expensive. So it is using an index seek and a lookup. Of course, this is, in this case, this is good for performance. Let's look at the next query. That is tab 76. This is the row compressed table. What SQL thinks is, well, the table is compressed. Now it has less amount of pages. Why not I scan the entire table? Interesting, because it again doesn't consider the overhead related to expanding the data. It is just looking at the amount of pages because it doesn't calculate the cost related to expanding the data. And the same way, if you look here, it says, I will scan the page compressed table. So when you execute these queries and you look at the profiler, there you see the first query that is uncompressed using an index seek, quite fast. The second query is slow because this is doing a table scan and this is doing a table scan, and it's getting slower and slower. So what we are going to do is force this index. So we are going to execute the same three queries, and we are going to say index test underscore C2. This is the index we just created, yeah, the index name test underscore C2. So we are going to execute these three queries, forcing the index. And when you look here, the cost is 12, 21, 24. Let's make a summary. SQL Server supports row and page compression. The compression ratio depends on the data and indexing strategy, how efficient SQL Server can do this prefix and dictionary compression. Also depends on how efficient it can take the fixed length column and store as a variable length column. If you have disk bottleneck, compression can help you a lot. When you consider compression, you should think about the benefits of compression, that is the reduction of IOs, and also the overhead related to compression, that is the CPU usage. Compression can also affect your DML queries, that is insert, update, delete, because when SQL Server stores the data, it has to evaluate and it has to compress. If you want to learn more about which tables, partitions, or indexes to compress based on facts like analyzing DMVs, the dynamic management views, I recommend you to attend one of our workshops. To find more information about our workshops, you can go to the website sqlworkshops.com and you can click on workshops. There you will find SQL Server performance tuning workshop, and to look at the agenda, you can click here. Thanks for watching this video. If you have suggestions, comments, feel free to send it to me. Bye.